Hello, and welcome to the We Need Water podcast. My name is Michael Brent, and I'm the Water Resources Manager for Cascade Water Alliance in King County, Washington. Cascade is a municipal water supplier providing drinking water to more than 380,000 residents. I'm glad you're here. Our topic today is NASA's GRACE mission. That is the Gravity Recovery Climate Experiment. As I understand it, the GRACE mission uses satellites to study freshwater resources all over the world. And NASA recently released a report on some of the new research results. Our guest today is Dr. Matthew Rodell, one of the study's authors. Welcome, Dr. Rodell.
Thanks for having me.
Well, let's jump right into this. Can you explain the GRACE mission? What is it all about?
Yeah, so GRACE, as you said, is the Gravity Recovery and Climate Experiment. And as its name sort of implies, it's actually a gravity mission first. It was conceived by geodesists as a way to measure Earth's gravity field in great detail, which you really can't do from the surface of the Earth very well. You can use gravimeters on the surface, but in order to get a map of Earth's gravity field, you really need to do it from space. And this is important for things like precise orbit determination for satellites. Every satellite needs to know exactly where it is and how it's going to respond as it orbits the Earth, for example. But after GRACE was launched in 2002, it was realized that some of the most important information that we could get from it was actually information on terrestrial water storage, which is the sum of all the surface waters, snow, ice, soil moisture, and groundwater. We can actually measure how that's changing in time based on the changes in Earth's gravity field that GRACE measures. The way it does this is actually two satellites, one following the other around the Earth. And the key measurement is the distance between those two satellites. As the satellites orbit around the Earth, changes in Earth's gravity field. So think about if there's a mountain range, there's going to be more mass in that mountain range. That means there's going to be more gravitational potential there. So actually, if you were standing on the top of Mount Everest, you would weigh a little bit more than you would standing down at sea level. Not that you would notice, but it's enough of a change that it affects the orbits of satellites as they orbit, in basically the
Okay.
vacuum of space. And so the distance between the two satellites, the two GRACE satellites, will change over time. And every 5 seconds, it's being measured by a intersatellite microwave radiometer that basically tells us the distance between the two satellites down to about the size of a red blood cell.
Mhm.
So this information can be used over the course of a month, together with the precise locations of the satellites. You put that into a supercomputer in a big regression routine that comes up with a new map of Earth's gravity field. From month to month, that gravity field changes, and those changes are mainly attributed to changes in mass at the surface caused by movement of water around the Earth. Think of like ocean circulation, atmospheric circulation, and then the changes in water on and in the land surface.
Fascinating. Well, so why does NASA care about Earth's water resources? Is what you describe almost makes it sound like the water resources are kind of a byproduct of the technology.
Well, it's actually in NASA's charter to study the Earth from space. And if you think about it, there's a lot that we can observe from space that we couldn't possibly do from the surface. So, for
Mm.
example, if you want to measure rainfall, it'd be impossible to place rain gauges, say 6 miles apart all over the entire surface of the Earth.
Hmm.
There's the labor intensity, the number of, the expense of it all, and maintaining them. And there are countries that wouldn't allow us to put them there. Um, but from space, we can make measurements all over the Earth. So that in this example, NASA's Global Precipitation Measurement Mission, or GPM, can measure rainfall globally at about a 6 mile resolution, and it does this about every 3 hours. Um, so that's one example. But in addition to precipitation and water resources, we have NASA satellites that observe things like crops and vegetation, wildfires, soil moisture, ice, atmospheric chemistry, ocean color and circulation, other processes, etc.
Well, fascinating. Let's talk a little bit about the findings of the research.
Yeah, so let's before I talk about the research, let's take a little step back first. So it's well established that the global sea level is rising mainly because of two things. One is that as the world warms, the oceans become warmer, and water expands as its temperature increases above 4 degrees Celsius. The other factor is that global warming is causing the Greenland and Antarctic ice sheets and glaciers around the world to melt, and most of that water ends up in the ocean. So these two processes are contributing to sea level rise. In our recent study, we decided to look not at the melting of the ice sheets and the glaciers, but all the other water stored around the world. So this is the fresh water that's stored in groundwater and soil moisture and surface waters mostly. Um, but the bulk of it is in these underground aquifers, the groundwater. When we
Mm-hmm.
looked at, going back to 2002 when GRACE first launched, when we looked at the changes in this non-ice terrestrial water storage over time, it sort of bounces along, and then you get to about 2014, and there's a sudden, steep, and abrupt decline. And so the pre 2015 time series, you're up here, and this time series is averaging down here after 2015, and
Mm-hmm.
it's a difference about 1.2 trillion metric tons of water, or about 290 cubic miles of water, and that's equivalent to about 2.5 times the volume of Lake Erie. That's the difference between the pre and post 2015 time series. We've used data from other satellites and models to construct time series going back to 1980, and we see that there are other episodes of freshwater decline, but none were as steep and persistent as this one that happened in 2015. And what makes it even more interesting is the timing. So you may have noticed, every year or so, NASA and NOAA put out reports on global mean surface temperature. And starting in 2015, we've had a series of the 9 warmest years in the modern temperature record, and 2024 is most likely going to be the 10th year in a row. And so it's the same 10 years when the planet's been warmer that we see this decreased level of terrestrial water storage
Mm-hmm.
around the Earth. And is that a coincidence? Perhaps, but signs are pointing to no.
Okay. Are you able to say what sort of percentage that this decrease represents in global freshwater supply?
Yeah, so it's actually a really tiny percentage of the total amount of water on Earth, and even a tiny percentage of the total amount of fresh water stored on the land. But with the way that gravity satellites work, they're not actually measuring the total amount of water at time A and the total amount of water at time B and subtracting the two.
Okay.
It's actually measuring just the change. So it's sort of like if you lived on a lake and you wanted to know the change in the volume of water of the lake, and you took some measurements, said, okay, well, it's dropped an inch of water. You wouldn't have to know the whole bathymetry of the lake and how
Got it.
deep it was and all that in order to estimate the volumetric change. You just take that 1 inch, multiply by the area of the lake, and you get the change. And it's the same sort of thing with the GRACE observation. So we don't really know, what it is actually as a percentage of the amount of water. I know it's far less than 1%. It's probably far less than 1/100%, but it is a significant amount of water when you look at it, compared to some of the major lakes or something like that.
Sh- Sure. And it happened. It happened over a short period as
Yeah,
well.
and just about over the course of less than 2 years between 2014 and 2016. And like I said, what really makes it different from other events like this is that it was a very steep decline. It was a deep decline, and it's persisted since then. It hasn't rebounded.
Hmm. Uh, presumably, presumably, this water is going into the Earth's atmosphere, right?
Well, it's actually been so. If we talk about how this happened, the decline in freshwater has really been sustained by a series of major droughts around the world. And in an earlier study, we looked at extreme water cycle events based on the GRACE data. So both droughts and pluvials, which are basically the opposite of drought, not necessarily a flood, but when there's more water stored on the land than normal. And what we've seen is that, especially since 2015, there's been an increase in the frequency and severity of these droughts and pluvials. So, and there's a very strong correlation with the global mean temperature. So as the Earth becomes warmer, there's basically this increase in frequency and severity of droughts and floods. And the new research shows that the net effect might be an overall drying of the land. But to your question, to be clear, the total amount of water on Earth never changes, or only tiny changes if there's like a meteor that brings some more water on
Sure.
the Earth or whatever.
Comment or something.
But if there's a loss of water from the land, it has to be balanced by increases in the atmosphere or the ocean, and mostly it's going to end up in the ocean. The atmosphere has a very, very small water holding capacity. It doesn't vary that much, but when you lose water from land, probably ended up in the ocean.
Okay. Are you able to see significant disparities between one part of the world from another? Are there some parts of the world that are seeing a greater stress than others?
Well, there have been, like I said, a series of recent major droughts. Around 2015, there was a huge drought in South America. They've since, basically in the Amazon, they've since recovered from that particular drought. But there have been other big ones. So the southwestern U.S. and Mexico have had a very dry period recently. Europe's been very dry for several years. Parts of southern Asia, including the Middle East, have been dry, and other parts of South America and southern Africa also have experienced some droughts. But the world's not drying everywhere. One thing I'll point out is that Central Africa has experienced a huge wet event over the past several years. It's just this absolutely massive wet event across a large swath of sub-Saharan Africa. So it's not uniform everywhere. Some places become wetter, some places become drier, and typically droughts don't last forever. But what we're seeing is sort of a net drying of the total global land surface.
Well, how about in the United States? Are we seeing areas with significant changes one way or another here?
Yeah, absolutely. Things change a lot in the U.S. We had a very wet period in the eastern U.S. Several years ago that's ended. It was dry around me in Maryland recently, but another big one is California. So we've heard about the series of droughts in California. And it seems like California is almost always in drought, but then they have these
Right.
big atmospheric rivers that sort of end the droughts, and that happened recently. There was heavy rain and flooding a year or two ago that ended a major drought in California. But one thing that's important to know is that even though that drought ended, and even though there was all this flooding, the aquifers that store a major part of our water resources that farmers really rely on, those aquifers never recovered back to the pre-drought levels. And if you look at a time series of the water levels in the California aquifers in the Central Valley, where we produce all this produce and everything, if you look over time, it's sort of like, I've heard it described as a tennis ball bouncing down the stairs. Like, it gets lower and then you have a
Yep.
recovery from drought. And it comes up, but not as far as the last time. And so that's sort of
Right.
what we're seeing.
One of the ironies of these heavy rain events that you were talking about is I know California in the past couple of years has seen tremendous atmospheric rivers, but as you say, when the water falls that quickly, uh, tends not to infiltrate and percolate down to the aquifers. So just kind of an unfortunate irony that there can be a lot of water, but it doesn't stick around long enough to do a lot of good
Yeah,
sometimes.
absolutely. And that's why you see governments building, infiltration ponds along highways and that sort of thing. You don't want the water to just quickly run off into the ocean. And it can cause a lot of damage when it runs off quickly, stripping soils and
Sure.
that sort of thing. And it also points to the importance of surface water storage like reservoirs, although there are other issues with reservoirs, as you know, where you are
Yep.
with when you consider things like salmon spawning and that sort of thing.
Sure. 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 Yeah. The salmon runs and sedimentation and all those sorts of issues. Well, you mentioned governments, though. How are governments around the world, or are they utilizing the information from this mission?
Well, governments move slowly, but we have seen that in some instances they've made use of information on aquifer depletion to make some difficult choices. So the two examples that come to mind are northern India, where there's been a massive decrease in groundwater storage that we observed using GRACE data, and that was caused by all the farmers pumping water to irrigate crops in an area that's semi-arid, and the Indian government has actually responded by putting in place some policies meant to make the groundwater last longer, essentially. And California's done that recently as well with the Sustainable Groundwater Management Act, which is going to forget when it goes into effect, but pretty soon. Also meant to preserve the California Central Valley aquifer and others that are critical for growing crops. The other thing we do is that we have a GRACE-based drought and wetness indicator map product that's distributed by our partners at the National Drought Mitigation Center at the University of Nebraska-Lincoln. We update that weekly, and it's downloaded by numerous many public and private stakeholders and other interested parties. Could be
Hmm.
farmers, insurance companies. I've even heard of people who monitor the migration of wild horses. So all sorts of uses for this data, and it also happens to be one of the inputs to the U.S. Drought Monitor, which is the nation's
Okay.
official drought map, which you've
Right.
probably seen in the back of USA Today, and it's also used by FEMA and other agencies to make decisions
Sure.
on aid.
Excellent. Well, that kind of ties into the next question: is where can people go to learn more about the Grace mission?
Well, the simplest thing is just to Google NASA Grace, and you'll get, I think the first page of
Okay.
results is they're all relevant. But yeah, there's the official NASA Grace website. There's the data that I talked about in the drought and wetness monitoring, and of course there's a Wikipedia page and that sort of thing. But all those
Sure.
have valuable educational information.
Excellent. Well, what's the future for the Grace mission?
Well, as I said, the original GRACE mission launched in 2002, and it actually survived until 2017, which was well past its original, 5-year design lifetime. The GRACE follow-on mission is actually the current GRACE, and it launched in 2018, and we're working on the next GRACE mission, which will be called GRACE Continuity, and that's planned for launch in 2029. Another thing that's exciting, though, is that the European Space Agency is working on its own gravity mission, which they would like to launch in 2032. And if we actually had two Grace-like missions in space, they would work synergistically to produce maps of Earth's changing terrestrial water storage at much higher spatial and temporal resolutions. So we're really excited for that possibility to work with our European partners on that.
Well, that sounds wonderful. Very exciting. Last question: what do you most enjoy about your job?
Well, there are a lot of things. I'm a scientist at heart. I always spent a lot of time outside as a kid and just doing my own little scientific experiments, and so I enjoy scientific research and discovery. I enjoy contributing to new technologies and satellite missions for NASA, and mentoring people is fun for me as well, and just generally doing something positive for the nation and for the Earth. And I work with some really bright, dedicated people, so that always makes it more more fulfilling as well.
Absolutely. Well, it is very valuable work that you're doing there. So thank you very much, and thank you for being here with us today, Matt.
Yeah, thanks so much, Mike.
And thank all of you too for being with us. I hope you enjoyed this broadcast. If you did, please like and subscribe and follow us on the socials at We Need H2O. You can also find helpful information about Cascade's water conservation programs at cascadewater.org. Have a great day, and remember, we need water.